Now Blair Newman is going to present, and let me introduce him. With strong tech expertise and 20 plus years of leadership experience, Blair Newman provides unprecedented insights into future of AI development and use. As Neuton CTO, Blair is engaged in overseeing business solutions as well as ensuring high-quality services are delivered to the clients. Prior to Neuton, Blair held various leadership roles at T-Systems North America, a division of Deutsche Telekom, being responsible for providing strategic direction and leadership in the areas of dynamic services, cloud computing, SAP hosting, application operation, managed hosting, and infrastructure services. Please welcome Blair. Your turn.
Thank you, Danilo, for, first of all, extending the invitation to not only myself, but to the Neuton organization to join today's event. It's certainly a pleasure to have the opportunity to be here, and I certainly want to extend my gratitude not only to yourself, but also to everyone that's in attendance today. So just by way of introduction, my name is Blair Newman. I am the CTO here at Neuton.ai. Maybe I like to sometimes say that we're kind of like the new kids on the block, unlike maybe some of the other participants that you've heard prior to me joining today's session. As we begin kind of today's discussion, I'd like to kind of start out by kind of reviewing just a little bit of our history from a TinyML perspective. So certainly, I think we all know that TinyML, as it's defined today, was kind of spearheaded by Evgeny Gusov as well as Pete Wharton. And at the time, they took a moment to begin to kind of define what does TinyML actually mean. And when you began to kind of reflect back at what they described, number one, they started off with what is the total amount of memory that would be consumed from a predictive model, let's say less than 100 kilobytes. And then you also wanted to make sure that the device that you had these models integrated or installed on, that they could perform for an extended period of time, in this case, years. And then when you think about the processors, they also define that. And then, of course, we wanted to kind of make sure, they wanted to kind of make sure that it was low cost, in that because these particular devices were going to be deployed into the field. One of the things that you don't see on this particular slide, but they also envisioned, was that there was going to be millions, if not billions, of devices that were in the field that would not only qualify as TinyML, but that we would have intelligence on these devices out there. And one of the things that we kind of looked at was, how can we help enable or drive this vision moving forward? So we kind of took it upon ourselves to say, okay, now let's take the baton and how can we now drive this even further? And that's been one of our core missions here at Neuton.ai. And I'm going to share with you as we move throughout today's discussion how we believe we've been able to now position TinyML for the future. So for ourselves, if you go and you take a look, as an example, just at Hackster.io, and you kind of look at what are some of the projects that are out there that you see at this time. And we, on our own analysis, took a look at a little over 200 cases that were out there on Hackster.io. And one of the things that we identified that a little over 95% of the cases that were out there were exceeding the 100 kilobyte mark that was originally set as it relates to TinyML, which kind of, let's say, brings to light that we're still struggling. The ecosystems, the community is still struggling with being able to produce models that are extremely compact and that qualify as it relates to TinyML, how it was originally defined. Very interesting, I might add. And now one of the things that I would like to ask all of you guys is, where are you at on your TinyML journey? What are the size of the models that you're building today? As I mentioned, if you go, you take a look at a number of published projects that are out there, the majority of them are over 100 kilobytes. But our goal, our objective is, hey, how can we improve upon this? So anything, if you were to start off and say anything below 100 kilobytes is what we would classify as TinyML, one of the things that we're doing is we're now saying, hey, how can we push the envelope? Not only go below 100 kilobytes, but also go below 30 kilobytes. How about going below 10 kilobytes? And we certainly believe that being able to produce a solution that enables the community to now build predictive models less than kilobytes in size without compromising accuracy will create a tremendous amount of opportunities for all of us, and then help fulfill that vision, actually push that vision forward that was originally defined in 2019. So here we go. So nowadays, when you begin to think about it, and I think it's important that we kind of level set, what does it mean when we talk about embedding a model? So for us, we begin to kind of look at a couple of different things. Of course, obviously, there is the machine learning model itself that has all of the weights, have all of the metadata, an associated calculator, as well as the necessary pre-processing that may need to take place in order to facilitate such predictions. Now, we identify this as the total footprint of intelligence. And of course, the amount of RAM that would be consumed by executing on those particular predictions. So moving forward, we kind of look at, first there was 100K, then we kind of drew a line about 30K, and then even 10 kilobytes. How we foresee TinyML moving forward is that we want to be able to enable everyone to produce models that are less than 1 kilobyte in size, on average, of course, with the total footprint as it relates to weights being less than 5 kilobytes and the total amount of memory consumed 10 kilobytes. By doing this, along with additional functions and features that we can certainly provide, we believe this should be the standard for TinyML moving forward. And we certainly encourage all of you guys to begin to take advantage of this. So size is one thing, but we also know, especially when you get to the point of now implementing these models into production, size is not enough. Of course, size is extremely important. It is the currency when it comes to TinyML, but you don't want to compromise accuracy as it relates to size. So with Neuton, this is also an area where we have found that we tend to excel. We're enabling everyone to be able to produce models of such size, less than a kilobyte, 10 kilobytes as it relates to the total footprint, but also you're able to do this without compromising accuracy. I'm sure all of you guys know, as you guys, I'm sure, have built numerous models throughout your experience, right? You start off with a fully connected network. More than likely, you're leveraging TensorFlow. You go through, you build your model. Then at that point, you need to go through a couple of additional steps in order to reduce the size of that model so that it can integrate into your device, into your MCU, into your sensor, whatever the case may be. And you take or you leverage some of those tried and true techniques, quantization, pruning, etc. When it comes to Neuton, you don't have to take those additional steps. So you're never compromising the accuracy of your model in order to reach a particular size so that you can embed that model into your respective devices. So in this particular case, we're giving you the best of both worlds, where you're able to achieve the best metric without compromising that metric at the smallest possible footprint. Needless to say, you're also saving on some additional labor because you don't need to take those additional steps. Now, when you begin to take a look at our solution, Neuton is a platform. It is an algorithm that we've developed internally in-house. So it's not based upon TensorFlow. It's not based upon some network architect search. It's something that we've developed over the last few years that enables all of you guys to achieve some of these various results that I've mentioned. Of course, when you begin to talk about AutoML, because this is the session that we're in, we've streamlined our pipeline. It's to 3 steps. We've automated everything in the background. So you drag and drop your data, you select your target variable, you start training, and then at that point, you can download and integrate your models. So we automate everything. And then also, you're able to achieve this with just 1 iteration. Typically, as you guys know, building models is an extremely iterative process. You go through, you try one particular function, you see if whether or not you're going to achieve the results that you're hoping for, and you continue through this process in order to reach your desired results. We're able to assist you in achieving your results in just 1 iteration. And then, as I mentioned, you're able to do this without performing any compression techniques along the way. Now, what are some of the benefits? What are some of the value that you receive by leveraging a platform such as Neuton? We consistently see that we're able to produce models that are oftentimes up to 1,000 times smaller than you would typically find with TensorFlow or other algorithms that you may be leveraging today. So when you leverage or when you produce a model with our platform, you're going to find that your models have fewer coefficients or neurons. It's significantly smaller in size, as I mentioned, up to 1,000 times smaller, and sometimes even more than that. And then your inference time is also going to realize some of the benefits as well. And we find that the inference time on our models are also up to 1,000 times smaller, faster than what you would typically find. And again, we don't leverage any compression techniques. And how we do this is we build all of our models, not from the top down, but from the bottom up, where you may normally take the approach of starting off with a fully connected network and then trimming that model down, leveraging those techniques that I've mentioned and that you've heard throughout our sessions today. Instead, we build all of our models neuron by neuron, performing cross-validation along the way as we add each particular neuron to the model. This enables us to produce the most compact model without compromising accuracy. By the way, we're in the business, we're all in the business, we're in the community of TinyML. The objective is to produce an intelligent footprint at the smallest capable size, because your battery, your real estate, that is your currency when it comes to TinyML. So we certainly believe that enabling the community to be able to produce these models, in this particular case, more often than not, less than 1 kilobyte. But actually, it gets better. What are the opportunities that being able to produce a predictive model or a machine learning model that is less than 1 kilobyte in size? What are the opportunities that are available for you? Now you have the opportunity to embed multiple models in a single MCU. But here's also something that I think all of you guys will get a tremendous amount of value out of. Our models are device agnostic. You're able to embed our models not only into sensors or ASIC devices or FPGAs, but also into 8-bit and 16-bit MCUs as well. So we're device agnostic. You can successfully integrate or embed our models into those 8-bit, 16-bit MCUs, and of course, 32-bit and 64-bit as well. Obviously, with having such a small footprint, you're going to consume less battery, less energy, and you're able to now drive more value, more functionality for your business out of a single MCU. So you begin to think about what are the possibilities that are available to you, to your organization. If now you can embed multiple models, as I mentioned, less than a kilobyte in size, even into 8-bit and 16-bit MCUs. So we believe that we are now positioning the TinyML community to continue to grow exponentially and realize all of the different potential that is out there and achieve those goals that Evgeny Gusov and Pete Warden set off for us to be able to have millions and billions of devices with intelligence. So as I mentioned, and I'm sure you guys know, if you're leveraging some of the existing frameworks that are out there, being able to execute or embed those models into 8-bit and 16-bit devices, it's not available to you. But guess what? Moving forward, leveraging Neuton, it is available to you moving forward. So think of the opportunities. Think of the capabilities. Think of what can you do now that you couldn't do yesterday. And here's a little bit of an eye chart, but we felt it was important to demonstrate and show some of the results that we've been able to achieve by leveraging our platform. Once again, it's a fully automated solution. You're able to achieve your results in just one iteration. And more importantly, you don't compromise any accuracy in order to achieve these results. Certainly, it's a little bit of an eye chart, and I certainly expect and anticipate that we'll have an opportunity to distribute this particular deck to all of you so that you can realize some of the value that I've been mentioning today. For now, as an example, a number of different use cases that we see out there. Oftentimes, we're seeing fault prediction, we're seeing anomaly detection, et cetera. But if you take a look just really quickly to line number 2, where we look to embed a model into a sensor to predict if whether or not an industrial drill would deviate or would begin to fail. And you can see by leveraging the platform, we were able to produce this model at 98% accuracy. You can see the size of the model is less than 0.5 kilobyte. The total footprint of this model, just barely over 1 kilobyte. And look at the amount of memory or RAM that's used. Extremely small. And when you compare that to if you were to use some of the approaches that nearly all of us have been using historically, leveraging TensorFlow Lite, performing quantization, you can see the significant difference in size between the two different models. In this particular case, Neuton is nearly 100 times smaller with better accuracy. So again, I certainly encourage you guys to take a look at these benchmarks. And I certainly expect that after the event, you guys will have an opportunity to look at this in a little bit more detail. Now, how do we do this? I kind of gave you guys some insight to this already. One of the things that I mentioned is that typically, as you guys know, when you start off and you're building a model, you start off with a fully connected network. You connect to all of the various features. And then after that point, you go through some approach of either pruning or you go through the approach of quantization. Well, as I mentioned, Neuton takes a completely different approach. We've actually flipped the paradigm completely on its head. Instead of starting out with a fully connected network and then trimming the model down, we build our models neuron by neuron, bottoms up. We only connect to the features that we've identified to have the highest predictive power. We then from there automatically grow the model neuron by neuron, performing cross-validation along the way. So we eliminate the need to perform any manual searches as it relates to defining any neural network parameters. And our patented algorithm leverages a global optimization approach. So just once again, instead of starting from the top, trimming down, we start from the bottom and build up. Every model is built for purpose. This is what allows us to build for you the most compact model with the highest level of accuracy in one iteration, creating significant amounts of opportunities out there for all of us to embed now in 8-bit devices, 16-bit devices, to be able to now embed multiple models into memory constrained devices because our footprint is so small. So again, what can you do now? So Neuton as an AutoML solution, it's a zero code SaaS-based solution. At no point throughout leveraging our platform will you be required to perform any coding. So we're enabling the community out there to be extremely well positioned from a TinyML perspective. So no data science experience is required, at least for myself. I always like to say, hey, I need a car. I need a vehicle to get me from point A to point B, but I don't necessarily want to be a mechanic. Of course, we need mechanics. And I'm not saying that data scientists are going to be extinct or anything like that. That's not what I'm saying. I'm saying that right now in our community, let's say you're an embedded engineer. That's your area of profession, but you want to bring intelligence to your devices, but you don't necessarily want to become a data scientist. Or from an organizational perspective, those data science resources are not available, etc. So by leveraging our platform, we enable all of you guys to begin to take advantage of machine learning and embed those devices into your ecosystem. Here is just a brief use case, is actually on the benchmarks page that I had up recently. Here is a use case where we leverage one of the silicon devices from an ST perspective. And you can see, once again, we were able to produce and build a model of minimal footprint. The model size is less than a kilobyte. The total footprint, again, less than 10K. In this particular case, a little more than 7 kilobytes. And the amount of RAM or memory that we use is significantly low. But as you can see, we didn't compromise accuracy along the way. In this particular case, we did a use case identifying by leveraging an accelerometer if someone was flexing or punching. And this is a real use case that was implemented. So as I begin to summarize, I would like to share with you guys just a few takeaways. Number one, we're taking a completely different approach to building models. We build from the bottom up. We're giving you the best of both worlds. Number one, they're going to be extremely compact. Number two, you won't compromise accuracy. We're finding that consistently our models are up to 1,000 times smaller than what you might find by leveraging TensorFlow, TensorFlow Lite. Our models can run on 8-bit microcontrollers, 16-bit microcontrollers, 32-bit microcontrollers, and you don't have to perform any compression techniques in order to realize the value of the size and accuracy of the models. No data science experience is required, and it is a zero-code SaaS-based solution. But more importantly, we make our platform available for free to everyone. So if, regardless as to where you're at in your journey from a TinyML perspective, certainly we encourage all of you guys, go to our platform, Neuton.ai. We have a free plan that's available for everyone. Go out, create new opportunities, validate the results that I've shared with you guys today. So I certainly encourage all of you guys to do this. Start today, go to Neuton.ai/start, and we'll get you going. So once again, I'd like to extend my thanks to all of you guys for allowing for me to be here. Certainly good to see everyone in person nowadays. So thank you very much. And it's a pleasure being here. And I look forward to having an opportunity to work with all of you guys and to continue to grow our community. Have a great day. Have a great afternoon.
So you mentioned that you are learning model neural by neural. And do you have a benchmark of this kind of architecture search on public data? So, I don't know, like keyword detection or MNIST or CFAR, like how do you compare this?
Yeah, if I think I heard your question correctly, so our platform doesn't, let's say, do an architecture search. So that's not necessarily our approach, but we do definitely have some benchmarks, and hopefully presentations will be sent out to everyone, and we'll make sure that the updated one does go out. But so no, our platform is not doing an architecture search. We only produce neural networks. And in building those neural networks, we go through and we identify what are the most effective features, or the most, which features have the strongest influence as it relates to predictions. So we do include, as an example, our feature importance matrix, where you can see those top 10 features that are influencing your predictions. We also include in our platform an explainability office, where you can not only you can dynamically change the value of any feature, and you can then see when you dynamically change the value of any feature, how it may influence your individual prediction. Also, we provide a lifecycle management tool where we will proactively notify you if your model is beginning to decay. So those were some additional slides that apparently didn't make it into the last deck, but that's what we provide. So we are providing those particular services or those particular functions as well, but we're not doing a network architecture search.
So does it mean that I provide the initial model topology and you do some kind of neural search there, or I still
Nope.
don't get like...
So in our platform, you will, let's say, upload your data set. You can drag and drop your data set. We don't start out with an existing structure at all. So based upon your data set, we build each model fit for purpose. And literally, it's built neuron by neuron. So we're not starting out with an existing structure at all.
Okay. Thank you.
I think it's like a follow-up question that most of the time what people do is we build a very complex model, we train it, and then we optimize it like it's a top-down approach, whether quantization, pruning, or other style of optimization. But so as I understand, what you're saying is you're doing a bottom-up approach, that you're starting with building a compact model from scratch, right? So there's no space for optimization later because you built it already optimized. So I think my question is just if you can elaborate on how can you do this bottom-up approach, like building an optimized model with that before even training or like,
Yeah, so some of it will be, let's say, a little bit of, let's say, our internal language. We use an approach which we call a swarm approach. So, and we also take an approach as it relates to, we do global optimization. So when we are, let's say, then building the model, we then identify which features have the, strongest influence as it relates to your target variable. And in doing so, as we then literally build each model neuron by neuron, as we perform cross-validation along the way, up to 10-fold cross-validation along the way. So then once the model has reached its optimal size, then there's no need to then perform any additional compression techniques. And that's how we ensure that the model is not only the most compact, but also highly accurate along the way. And we also include in there some overfitting control as well.
Thank you for the great presentation, and thank you for sharing the pricing plan. This is unrelated to the technical stuff, but so what's your business model since this is free? Like, how are you making money?
Yeah, so our platform was designed to be self-service. So any event that our customers or our partners may need assistance with, let's say, a use case implementation, then we will work with them from a services perspective. But as it relates to just leveraging our tool, our platform, we don't charge for the use of our platform. But if you need assistance with implementing your use case, then we will include, if as necessary, a data scientist, a data analyst, an embedded engineer, because what we found is that, at least specifically in the TinyML space, that embedded engineer, let's say, may really be a data citizen. They haven't necessarily, all of the necessary prerequisite skills to be able to build a model and then integrate that model. So we'll charge on a use case by use case basis with our partners or our customers.
Thank you.
I mean, what is your definition of a neuron?
I'm sorry?
What is the definition of a neuron? You talked about building a model bottoms up, neuron by neuron. And so, can you help us understand what you mean by that?
Yeah, so the weights are the coefficients that you would typically work with when you are using TensorFlow, PyTorch, et cetera. I mean, we are basically taking the same approach, except that we're not starting out with a fully connected network. So if you're using TensorFlow, you're starting out with a fully connected network. You're connecting to each individual feature, and you're starting off, depending upon how many features you have, with, let's say, for example, you have 100 features. You're going to, each layer, well, you initially will connect to each feature. So for us, in our approach, since we're taking bottoms up, we're only going to connect to features that specifically have, internally, we've patented our algorithm to the features that we believe have the highest weight that influences your predictions. All right?
Very good.
Thank you.
Thank you so much, Blair.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, Deep Lite, Qualcomm, and Syntiant. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving TinyML forward. Gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, Sensational, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymix, HOTG, Imagimob, ITMIS, Lattice, Nota, OmniML, Pixart, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support and, more importantly, for them being part of this community and driving it forward.